All right, so we've got an example using moment of inertia. And remember, moment of inertia is that property of an object that resists change in motion. So it's going to resist starting up, slowing down, changing direction. It just wants to do whatever it was already doing. And so we've got Fred pushing an empty merry-go-round, and he applies a 300 Newton force at the edge of a 40 kilogram merry-go-round. Has a radius of 2 meters. And the question is, what's the angular acceleration of the merry-go-round? And so we have the equation for angular acceleration. And we have gone to the list and looked up the moment of inertia equation for a disk, because a merry-go-round is basically a solid disk. We have, from our problem, we have the mass, the radius, and the applied force. So starting off with torque, because we need to find our torque. Torque is force times distance. Plug that in, and we get 600 Newton meters. Then we find our moment of inertia, 1/2 mr squared, and we get 800 kilograms per meter squared. And then we can plug both of those items into our angular acceleration equation and get 7.5 radians per second squared. So where it becomes a little bit more meaningful is if we look at what happens if you add some more mass to the merry-go-round. So we're going to put a 60 kilogram friend on that same merry-go-round. We're going to use the same force as before, and we're going to have the same equations, but this time we have to add in the moment of inertia of the friend. So the two moments of inertia add up, because remember, a moment of inertia is the sum of all the masses and all the radiuses from the center of rotation. So we have to go about and find the moment of inertia for our new friend. And so we use that same equation. And we can use the same equation because we're just going to consider him to be just an additional point mass to the big disk of the merry-go-round. So you find his moment of inertia, add it to the moment of inertia of the merry-go-round, and then we can use the same equation. And what we're going to find is that the angular acceleration has decreased from the situation without the kid on the merry-go-round, so that makes sense. There's less acceleration now that we have some more inertia. Bye-bye.